Okay, hello everyone. My name is Sebastian Chwilczyński. I work at deepsense AI as a machine learning engineer, and today I will talk to you about things that I wish everyone knew, but also I'm pretty sure that you will learn something new today, so stay tuned. We will be talking about methodological errors, so the nasty errors that no one likes when we work with data. Okay, so to start, we need to know what errors are we talking about. So the methodological errors do not raise exception. That's the worst part about them, and they are around us until production verifies us. So in the programming error, we did something that is inappropriate in programming language, and it detects it and raises an exception. So we see we did something wrong. In the methodological error, on the other side, for example, we have this data for samples are correct, and last to get -1 value, it is probably magic value, denoting something weird that we don't know. But when we don't inspect this data, basically, and train linear regression, it's happy with that, the model will be trained. So these are the errors we want to prevent. And during this presentation, I will be using synthetic data, and this will be marketing-related problems, just to be sure, just to know the actual influence of the use methods. Okay, so let's talk about methodology first. So basically, we have a problem. We need to select a methodology, which is a set of steps that will lead to a solution. So for example, problem, forecasting results of future sales, and methodology, very simple, very simple one, get data and train XGBoost. And when we implement this methodology on the problem, we get a solution. And what happens next? We put it on production, and it may results might vary drastically from what we predicted. So as an example, we predicted that if we spend 20 million on marketing, we would get 10K new customers, but it turned out we only got 5K. So this is pretty bad result. And this deep talk will be all about how to prevent this. And basically, it will be all about challenging the methodology you choose. So we should be like a kid, ask about everything. Are the results stable? What would happen if we had different sample, if we had different sample size? What if we do analysis on every subpopulation separately? Next, is the methodology correct? Basically, are the assumptions fulfilled? Like, they will never be fulfilled, but how much are they violated? And is this methodology best? Maybe research is happening, and like problems that seem solved, missing data or future importance, research on these things is still happening, and you may be shocked that there's a lot of new tools that can be used for that, and people stick to default methods. So our methodology may be basically incorrect. Okay, so we will talk about methodologies, and we will talk about 4 problems that I encountered when working with tabular data. We will try to answer questions given by company to us to solve them. And throughout these questions, we will learn all these main key takeaways that I want to cover. So we will start with the question, how many new clients will we get this year? This is a very good question that we can get from company when we work from data. And the setup looks like this. We have training data, which some X and become customer is our target label that we want to predict. And we have production data in which we do not see if someone became a customer or no. And the analyst is interested in knowing how many people will become our new customers. They are not interested if customer 1 will became a new customer, but in general, how many of the entire population will become a customer. So we think, okay, let's do this. I can do this. I know XGBoost. This is the best methodology ever. Use XGBoost for everything. So we will train XGBoost on the training data, take the production data, basically predict if someone became a customer or no. And okay, we will hopefully predict that 20% of people will become our customers. And this approach is called classify and count. And in general, this problem is called quantification. It's a separate type of problem. So now we train the classifier, and is this classifier optimal? So in this data that I've shown here, the true ratio is 50%. And we have two classifiers. And which quantifier is better? Because we want to predict the proportions in the data, not the individual predictions. So if we look at the first one, we can see that this one made only 18 errors, basically here, 10 and 8, but it predicted y had 1, 18 people, and y had 0, 22 people. And our ratio is 20 to 20. So it is better classifier than this one, which made 20 errors, but predicted correctly 20 examples of class 1 and 20 of class 0. So you can see with applying blindly this methodology and not doing more research on basically what problem we are trying to solve and checking if people figure out what can go wrong, we may get wrong conclusions. And yeah, the thing is that optimal classifier minimizes false positive plus false negative, but quantifier minimizes the difference between them. Okay, so now let's see it on the real data, like our synthetic data. So here is a small experiment. Again, making experiments is very important in working with data. So we make a data set, it's synthetic. We know that is 80% to 20%. Then we train XGBoost, and then we train our quantifier. And eventually we just compare, we calculate the proportions got by XGBoost and proportions got by our special quantification method that I will explain in a second. And after running this simple experiment, we can see already that XGBoost predicted 76 to 23%, and we know that our proportions are 80 to 20%. And our special quantification method predicted almost perfectly. So it's just by 3% different, but this may be big. This make big change when we predict that 3% more people will become new customers. It's very positive and good information. Okay, but there's another catch, because here we just make experiments and we do one data set and we compare these ratios to the ones we know. But actually, this is again wrong. And if we do more research and read about this quantification problem, we learn that basically data set is just a single sample for quantification. And on this previous slide, we can see a word's additional data set shift. Basically, data set on production may have very different distribution and so on. So we cannot evaluate model for quantification on just a single data set because it's a single sample for this kind of problem. And who evaluates classifier on one sample? And to evaluate quantifiers for this kind of problem, we should use special protocols, for example, artificial prevalence one. So we have train and test data, and we artificially subsample from this test data set with different prevalences. And we calculate error for those, and we average it out. And we plot all this on plot that is called diagonal plot. And the diagonal line is the perfect quantifier. So when true prevalence is 0.2, our quantifier predicts 0.2. That's perfect. And we see that for this classify and count method, which we try to do with XGBoost, it is not the case. Here, true prevalence is 0.2, and we predict more than 0.2. So that's pretty bad. Okay. And generally, this is called learning to quantify, and this is highly underrepresented topic in ML community. It's pretty hard to find any materials, and there's just one Python package, QuiPy, that I found. I wish there was a scikit-learn implementation of quantification method, because they, as you saw, may bring many improvements. Okay, so that was the first thing. Again, we wanted to predict how many new clients we will get this year, and we started with a baseline of XGBoost, and we predicted each row separately. It turned out to be not optimal, because there is a separate field called learning to quantify. Sorry. Okay, next topic. Company got a question to us: how effective is our new client program? They introduced new program, which let's call it a factor, yeah? So there's a factor that they tune, and how this factor influences the sales. So this is, again, a very good question that we want to know. To simplify things, we'll use linear regression, and we want to get the influence of factor on sales. And again, this is synthetic data. We know that this factor is 7.5. So if we increase factor by 1, we get 7 times plus to the sales. And our company want to know that. In reality, we don't know it. Yes, so the catch is that we have some missing values. So if we run it, it will just raise exception because it is we cannot use linear regression in scikit with missing values. Okay, so we need to handle it somehow. So meet our fighters. These are missing data imputation methods. So we need to figure out what to impute instead of this none. And there are a ton of methods. I will not cover all of them. I just want to say that they are different. And these quotes are from the book on missing data imputation. And we can see mean imputation is told to be avoided in general. Regression imputation is also told to be bad. Stochastic regression imputation is good. Mean imputation is this, so we just predict the mean value. It looks wrong if we take a look at here. Regression imputation, we just train linear regression and predict. And stochastic, we train linear regression plus we add noise to those predictions. So this method's different. The key point is just there are many methods for mean data imputation, and in research, in books, people write what to use and what not to use. And now we meet our opponents, because the data may be missing differently. And we have 3 opponents. First, data misses completely at random. We just do a random choice and assign none. Then data is missing when only for 25% of biggest X values. And the third pattern is that for the biggest X values, Y is missing. So these are completely 3 different situations on which our methods will behave completely different, what you will see in a second. And again, we have this synthetic data, and we perform experiments. And here, new factor is introduced, confidence interval. So we will measure uncertainty of every of our method, and we 10,000 times perform the simulation. Okay, so round 1, missing data is completely random. So we can see there is no clear pattern. And with mean, of course, data is from standard normal distribution. So we get this peak at X equals 0. With regression, we get this green line, and stochastic regression are these red points. These are the imputed ones. And on the left, we can see results. Our goal is to get 7.5. So no method get exactly 7.5, but stochastic regression get pretty low coefficient, which is weird. Before we read that it's the best method of all of those, but you can see that it introduced a lot of noise because X is a little bit noisy and Y is much more noisy, and we try to predict X using Y, so it introduces and then add noise, so it basically adds much more noise, which lead to underestimation, and even the confidence interval doesn't cover it. But we change the data missing pattern, and situation completely changes. So now just the biggest X values are missing. So these values are missing, and we can see regression imputation generated very line with a big slope, yeah, and the coefficient is 9.30 because it didn't see all the data to the right. We imputed it having just data on the left, and the slope was much bigger. Yeah, so it performed poorly in this case. Mean data still not the best, but this time stochastic regression performed really well. And again, confidence intervals. Now we kind of know all our uncertainty thanks to this, and that's very important. And the round 3, Y is missing just for 25% of the biggest X value. So this is the worst case for the mean imputation. So not X is missing, but Y is missing, and we try to impute Y. So we can see that for this mean imputation, basically it just predicted mean of those blue points. So it is much lower because we remove the biggest y, and our final slope of the coefficient for the this factor is just 3, which is in fact much bigger. And those methods predicted quite well. And now, fun fact about confidence interval. So these mean and regression methods, they generate much narrower confidence interval. Their width is just 0.5, and that's pretty. We want confidence interval to be a little bit wider, which is here for stochastic regression, and stochastic regression covers the true mean, and we are like more likely to get this true mean in real data. Okay, so we wanted to test many methods with many scenarios, and we see that they can perform completely different. So it's very important to test those different scenarios in real life. Okay, so what we basically did here was called method multiple imputation, because we performed 10,000 of experiments, we averaged the results, and we did confidence interval. So this is like we can find most of the red lights doing this. Basically, we get uncertainty measures that are very important, and because knowing that mean maybe 7.50, it says basically nothing, and we get much better estimates of values of interest because mean of many measurements is closer or be closer to the true mean. Okay, and generally missing data problems this is much more complicated than it seems, because we can have different missing data mechanism, different missing data types, and something called ignorability. And remember, data is what we feed algorithms with. So if we make mistake at this point, this basically makes the whole later analysis pretty bad. There's much to cover, but there are also many materials. So there is a guy on YouTube, Mikoronko, that has just 1 hour series about missing data. Very nice. You can check out books, and you can check out also scikit-learn on this multiple data. But again, this is simple problem, but we can cause many problems to our analysis by not doing any research on that. Okay. So again, we wanted to predict factors. We had missing data, and it turned out if the data is missing in a different way and we use different methods, we get completely different results. So it's very important, again, do experiments, measure and uncertainty, repeat. Okay, so we move further. Feature selection. Which product characteristic matters the most? And yeah, we have this data set. Our product has 12 characteristics, and we measure how satisfied are people with products with different characteristics. And the company want to increase this satisfaction, of course, and they ask you to get the feature that improves this satisfaction the most, because they want to invest in it. So the output should be invest in 12 features. Okay, we again have synthetic data, and we created in by ourselves, so we can do what we want. And I created it in a way that a feature with bigger index has bigger coefficient. So basically, feature 12 has coefficient of 12, and it's the most important one. So we know this a priori before running the analysis. So what we do, we know that, okay, if we do linear regression, we get regression coefficients, and the biggest coefficient is the most important. Okay, job done. So we do just this, very few lines of code, and we get that the biggest influence had 11 feature. Why? Because data is noisy. We just get sample. We do not get population. So it's not that simple. By just taking this one measurement, we may get wrong results. And how bad it is, it depends, of course. Because if we increase 11 feature by 1, the sales will increase 1 less than we would increase 12 feature. So now we should ask in what units sales are expressed. In millions, this is pretty big loss. And do we measure them a year or a week? Yeah, so that's that's pretty important to make correct conclusions. So again, measuring uncertainty basically to the rescue. So we changed just one thing. Instead of doing one measurement, we performed bootstrap on our sample. And we measured rankings of these features 100 times, and we plot confidence intervals. So uncertainty, again, is pretty important. And from the analysis, we can see that even the 9th feature sometimes was first. So it could happen that we suggest to invest in the 9th feature. But if we show this, if we see this, now we have much more detail, and we can repeat the experiment with just those 4 features, because maybe there is some interactions between these features and these less important features, and this makes analysis harder. We may argue to collect more data, and most importantly, we do not make false conclusions. We know, okay, we still have some uncertainty, we need to make more analysis. Okay, and now company came back and they want to identify all informative features, or features that matter and they should invest in, because now the product has not 12 characteristics, but 500 characteristics. And the method we could use is lasso. So we can use lasso regression and check out the coefficients of every feature, and lasso may zero the coefficient out. So if coefficient is zeroed out, it means it's not important. So we don't make one measurement, we make many experiments, bootstrap or so on. And for every experiment, we measure if feature was selected or no. And by selected, we mean its coefficient was bigger than 0. And you can see that, okay, features with -2 coefficients were selected always, but features that get coefficients from -2 to 0, they were not always selected. And sometimes features with 0 coefficients were selected. So if we made just one iteration of this lasso, we again may get wrong conclusions, because falsely some feature with 0 coefficient may be selected because just of the random noise. Okay, and I'm not saying feature selection are bad, just remember about bootstrapping, about confidence interval. And the next thing, again, do research and check, because there are crazy new methods on feature selection, and like projection, predictive variable selection, which is much more robust. And just check if research didn't provide new, better solution than this linear regression feature selection, which is pretty old one. Okay, and the last question, who should we target with our advertisement? So company can send ads only to 20% of clients, and who should we send them? So probably to the ones that are most likely. So this is similar scenario to the first one. We have our training data with labels and production without labels, but this time we just want to indicate what clients are the most likely to buy a product. So client 0, client 12, and so on. Again, okay, let's use our favorite methodology, XGBoost. So we just predict, XGBoost can predict probabilities. So we use it and we got such probabilities. And now from these probabilities, we select 20% of most likely clients. And if we do this, we will get 8% difference between predicted and actual sales. So this is, again, this simple experiment. We initialize classifier, we predict probabilities, and we select 20% of the best. And the true mean in those 20%, in those best 20%, 47% of people opened the ad, became a new customer, but our model shown that just 39% will become new customers. So after 2 months, we may get shortage because we will get more customers than we predicted. Maybe it's a good, but like we don't want to have shortages and make customers wait. So this problem is called a model calibration. So within a group of people for whom the model predicted 80%, the average of the real data is different than this. And basically, this can be solved. There are separate methods for calibration, sigmoid calibration, isotonic calibration, or we may use naturally calibrated models. But this is not that simple, because we plot, okay, and what we measure, a good calibration is called a reliability plot. And again, diagonal line is perfect. And we can see that uncalibrated XGBoost, the blue one, is pretty off. The yellow one with sigmoid is less. The green one with isotonic is the best. And here we train logistic regression. And we may think, okay, logistic regression seems to be closest to this diagonal line than all of those green other lines. Why not to use it? Yeah. But the next point is to look on the problem from different viewpoints. Yes, logistic regression is calibrated the best, but it is also the worst classifier at the same time. So if we use this, if we use logistic regression to predict the probability of someone becoming a new customer, we will make 20% fewer new clients. And here is experiment doing it. So we just iterate over all our models we trained and do the same. We calculate predicted mean of the model and the true mean. So we see logistic regression predicted 28%, true mean is 29. So it's a good calibrated, but we get much less customers than we potentially could get. And XGBoost with isotonic calibration get much more clients, so we will get more sales, but also was better calibrated. So here we looked on the problem from two viewpoints, from the calibration, but also from the performance. So we should be looking from the two viewpoints. Okay, and yeah, as with everything that I told you, be careful, because this calibration method has weaknesses, and I make assumptions that are, of course, never correct. So with logistic regression, it is bad classifier, we know this. With sigmoid calibration, we may get poor fit if the probabilities doesn't fulfill some logistic distribution, and with isotonic, it may overfit, it requires large data sets. So again, be careful. Okay, and to sum up, there are my 4 key takeaways. So I covered 4 problems, but maybe it was not that much about the problems. It was most about what to do to prevent problems and how to do this. So first, like topics that seem solved are not. This quantification problem, missing data problems, feature selection, these are still highly researched topics. So if you have if you put something on production, make sure that this is the on the edge research and uses the best method possible. Next, uncertainty. I made thousands of bootstraps, thousands of confidence intervals. These are very helpful. Maybe they will not confirm you that you're doing a good job, but they will warn you if you do a bad job. And again, look at your problems from as many viewpoints as possible. So with this calibration, we cannot just look at calibration, but we need to look at calibration, but also performance. And simulations, real data is really wild one, but start maybe from some simple synthetic data that more or less follows the distribution of your data, and this can help you understand the problem. When I was preparing this presentation, I created a ton of these synthetic data sets, and I really understood it much better, what may happen in real data. Okay, so that is everything I got for you. Thank you.